So I'm here to talk to you about a single-family home in PEI. And I'm making an assumption that people here have some familiarity with the Passive House Standard, but I will start with a little bit of a Passive House 101 to make sure that everybody understands how powerful the Passive House Standard can be. And I just want to start by saying we have a lot of development going on in our city, and it's a sign of progress. We go around and there's cranes and construction sites everywhere, but I find a lot of it disheartening because I'm making a wide generalization, but a lot of it isn't very sustainable. And I think we need to look at buildings as an opportunity to reduce carbon emissions instead of looking at the added costs of sustainability. There's a lot of room to improve. So here's the Passive House 101. On the left-hand side is why we do it, and on the right-hand side is how we do it. So obviously, we all know that Passive House is very sustainable. The Passive House Standard is based on very low energy consumption, and by conserving energy, as much energy as we can, we build a building that is inherently net zero ready, so that if we add usually just a small amount of renewables, we have a net zero house. We do it for comfort and health. A passive house maintains about 20 degrees Celsius all year round. Sometimes in the summer they get a little hotter, but we work to mitigate that. They're draft-free, the air quality is exceptional, they're very quiet. And as Wayne was telling us earlier about the Billigan House, they're very resilient. So no matter what polar vortex or weather bomb is coming our way, if you live in a passive house, you're not going to suffer. And we build them because they're affordable. And that's arguable because we live in a society that really promotes instant gratification. But later in my presentation, I'm going to tell you about how if you take the long view, it's actually the cheapest way to own a home. They also offer you security from rising housing or rising energy costs. There's less maintenance, and you don't have to pay as much to service your mechanicals or to replace them. So starting on the far side, we do this through management of solar energy. So we site the house for optimal solar gains, and we size the windows and locate them strategically to optimize the solar gains. This is why there is a lot of confusion about the difference between passive house and passive solar. This is really the only overlap, is that we use the sun in both. So moving on, if you're going to build a passive house, you need to use high performance windows and doors. These here, at least, are always triple glazed, and typically they would have coatings and gases to kind of further refine the performance. We have an airtight envelope. We're meticulous in the detailing, and we test the airtightness with blower door tests periodically during construction at key stages. Continuous insulation, obviously much higher R values than in a typical home. And thermal bridge free so that there's no gaps or weak spots in the envelope where there could be heat losses and also cold spots that cause condensation. And finally, fresh air through heat recovery. And so we use a very efficient HRV and increasingly an ERV, so that's an energy recovery ventilator to deal with high humidity inside the houses. Okay, so When we talk about passive houses, people often launch right into what's your R value and what's your assembly, and when we're designing a passive house, we kind of have no preconceptions about those things. We have to make an educated guess at it by building an energy model that starts to examine that. So this is an image from my energy model for the house I'm going to show you. It's in Imperial. So this house is designed to the European passive house standard, but it is not in metric. So the numbers you see up there are the equivalent of the metric standards. So for example, the 4.75 kilobTUs per foot squared per year is the same as the 15 kilowatt hours per meter squared per year in the European model. So the column on the very far right says fulfilled. That tells you whether or not your house is actually a passive house. So once you've put in all the specs about everything, your location, your orientation, everything about your windows, the dimensions of the building, your mechanical systems, you come back to this page and you see whether you're a passive house. And if you're not a passive house, you start manipulating variables until you are a passive house. So you can see that this house has met the space heating requirements, and cooling is not an issue. I guess I could be pointing over here. We made an assumption about the air tightness. The builder on this project, they've done a lot of passive houses, and they were confident that we were going to hit 0.4 air changes per hour because they've never gotten more than that. So typically, I would model a building with 0.6 air changes per hour. And you know, probably if I was doing this one again, I might as well, just to have a bit of a buffer. And you can see that we have not met the target on the primary energy. So primary energy is all of the electrical loads in the building. So not just heating, but hot water, lighting, appliances, everything. And in the German passive house standard, actually in all passive house standards, there's a factor called the primary energy factor. And what this means is, depending on where you are in the world, your primary energy allowance is actually based on how much carbon you're emitting. And so we have a bit of a penalty here because our grid is dirty. So it can be harder in Canada to hit the primary energy target compared to other places in the world. So we're a bit over on this target in this house. And these people are not certifying. There were a couple of things that we could have done to certify or to hit the target if we were choosing to certify. And I didn't really mind because I'm expecting these people to put solar panels on the house. I didn't model them because I wasn't 100% sure, and neither were they. But I think that they will, and then it's no problem. So this house is built by Trout River Homes. They are a PEI builder, obviously, that has been building passive houses since about 2012. And our site is pretty ideal. It's a field with no trees. It's flat. We could point the house any direction we want. So in terms of our solar, capacity, we're great. The house itself is a very simple two-story, 40 feet by 32 feet rectangle with a garage on the side that is outside of the thermal envelope. It's about 2,500 square feet, but the treated floor area, which is, I can't tell if you guys can see it, but there's a sort of lighter blue shade inside each of the houses, and that's the number that our energy model bases the heat load calculations and the ventilation calculations. So we base those on a very particular number. Wake up. No? You can slide it ahead. Okay, so this is a comparison of the building details of the passive house and sort of standard code-built house. So it's a slab on grade, and it's fairly, the actual slab is fairly similar in both cases, but the passive house has 10 inches of EPS insulation under it, and you can see that that wraps under the footing and up the side of the footing, whereas in the code-built house, we have usually 2 or 3 inches maybe of insulation under the slab. We don't insulate typically under the footing, and if the builder feels like it, according to code, we're supposed to do this, but it often gets missed. You might have some perimeter insulation just vertically around the side of the footings. The code house just has a standard 2x6 wall with bad insulation. The passive house has what's called Larson trusses. And Larson trusses are, they're like site-built TJI joists. So you have a 2x6 and a 2x4, and they're offset by about 15 inches in this case. And they're fastened together with a strip of OSB, and then that whole thing gets packed full with dense packed cellulose. On the outside of the Larson truss, there's your sheathing and WRB, your water-resistant barrier. On the inside, we have a vapor barrier. In this case, it's Intello, which is what's called a smart vapor barrier. It allows any vapor that gets into the wall to dry to the exterior, but doesn't let any in. Or rather, it dries to the interior. We have a service cavity inside of that for electrical and plumbing. Our code house just has a standard double glazed window. We modeled it as vinyl. And the passive house has Gaulhofer Energy Line 85 windows. These are European windows, and they're bought in Ontario. When Trout River Homes was starting to build passive houses, not very many suppliers carried any products they could use, so they've got a good relationship with Herman Timber Frames, which is in Ontario, and they still source most of their stuff from them. The roofs in the two houses are fairly similar, although we have a bit more of a raised heel on the truss in our passive house. And the passive house has OSB fastened and taped and sealed to the underside of the trusses, and then a service cavity below that. So the OSB is the vapor barrier. So you can just, I'm sure you've read by now, the numbers on the sides. The passive house costs about $375 a year to heat, and it's responsible for just under 6,000 pounds of carbon dioxide a year. The code house is substantially more than that, with $2,350 a year for heat. That's not including electricity, just heat in both cases, and 23,000 pounds per year of carbon dioxide. So building a passive house saves a lot of emissions. Excuse me. Oh, it did it. So now some pretty pictures of the construction sequence, because they're fun and because Trout River Homes builds their house a little bit differently than a lot of builders. So they pour the slab, and I don't actually have any photos of the slab under construction, but it looks like a slab. And then they build the walls on top of the slab. So they build everything on the flat. So build the Larson trusses, sheathing, and WRB, and then they kind of pile them off. Oh, shoot. Back. they pile them back off on the side. They also frame the roof and sheathe it down on the ground, and they do all of the nitty-gritty air sealing and stuff down on the ground so that they don't have guys up on scaffolding doing tricky stuff. And then they have crane day, when it's one whole day, the crane is on site. I think it's a long, stressful day, and they put it all together. I think in this case they framed the garage on the slab, and then they had crane day, so there would have been sort of 3 walls of the garage, and then all of the other pieces got snapped together. And that's a view from inside the house. You can see this is shortly after crane day. The floor trusses are in place. They are bolted to the 2x6 portion of the Larson truss, and then the chase walls are built inboard of those afterwards. And you can see that there's kind of a flap of the vapor barrier material that they put in place before putting the floor in, so that they don't have to work around that. They get a continuous vapor barrier easily. And on the other side is a close-up of the window. And if you guys are familiar with Natalie Leonard, most of you, anybody who knows about Passive House in Nova Scotia knows Natalie Leonard. Most of her projects, probably all of them, you'll find the window installed in the plane of the sheathing as far to the outside as possible. Trout River Homes sort of adheres strictly to the German standard, and the Germans want you to do this. They want the window in the middle of the insulation. Thermally, this is better, but in terms of management of water infiltration, it's a lot more challenging. So Trout River is really great at it. They've never had any issues, to my knowledge, but it's a vulnerable spot it's a vulnerable intersection. Okay, now we're here to talk about money. And I have to give a disclaimer, I'm not an economist. I know a lot more about the nerdy building details. But if we're gonna get people to build passive houses, we have to talk about the money. And here we are. I was really, really excited because in the fall, the municipality, or I guess the city of Charlottetown, approached Trout River Homes and asked them if we could do a financial case study of one of their houses. And so they asked me, and we said yes. And so we sat down and compared what we think a code-built house, if it's built to this same design but using code-built assemblies and components, would be. And as you can see, the house that we built looks like it is 19% more than a code-built house. Now, that feels really high, given what we know about what it should be, I guess what other projects are in this area. And honestly, the code numbers are something we sat down for 2 hours and made up. Like we don't really know, so I'm inclined to think that we underestimated the code values, but perhaps not. I don't build in PEI very much. This is my first house in PEI. And at $491,000 for the house that was built, it works out to a little over $200 a square foot. I think it's about $203, which is in line with a lot of construction, new house construction, that we do in our practice of code-built houses. So the kind of analysis that they wanted us to do is called CFAR, Sustainable Energy Efficient Facility Asset Renewal. And you can see on the screen a comparison of the energy costs for the two houses. The green is the passive house and the red is the code-built house. The CFAR analysis is, it spans 60 years. A lot of other methods of analysis, of economic analysis, don't look at that long a time frame. And we think it's important that they do, because that's when you really see the economic picture clearly. This slide is really interesting to me. It might be less so to you guys, but in our office we do a lot of renovations, and this is the maintenance and repair and service costs associated with the two houses. And you can see, it kind of goes along status quo for a few years, and then there's a spike. And anybody who owns a house knows that's kind of how it goes in terms of things break. Everything sort of breaks all at the same time a lot of times. And so these intervals where things peak, those are likely either mechanical breakdown or replacement or window replacement, something expensive. And you can see in some of them, the conventional house is more expensive. In some of these spikes, the passive house is more expensive. I think that one around 30 years, it's probably the passive house windows need to be replaced at that point. They wouldn't need to be replaced before that. When you think of a typical vinyl window, 30 years, they're pretty beat up, but in the passive house, they're still not in bad shape at that point. And so the goal of the CFAR analysis is to give you the total cost of building ownership for the lifespan of the building. And they look at 60 years because they think that they define that as the sort of typical useful lifespan of a building. At that point, it's either going to be knocked down or it's going to need a really significant upgrade. And so I think what's interesting in this is where the two lines crisscross. Obviously, the passive house costs you a bit more for the first few years because your mortgage is a little higher. But they do diverge, and the passive house clearly costs less in the long run. So looking at a few critical stages at 12 years, which is the average length of time a person owns a home or a family owns a home, the passive house option has saved you $21,000. I should back up and say the factors in this are everything they could think of that you would pay for a home. So your mortgage, interest, maintenance, utilities, and it even factors in taxes on greenhouse gas emissions. So it's quite comprehensive. And so back to this, at 25 years, which is the term of most mortgages, the passive house has saved you almost $100,000. And at 60 years, the passive house has saved you $563,000. So you don't just have costs, you also build equity in your property. And so that's what this graph is about. They both kind of follow the same pattern. It's not that surprising, but it is encouraging that the passive house diverges a little bit, so they're recognizing a little bit of benefit to the higher quality building. And this is my favorite slide. It shows you the total cost of building ownership when you factor in all of the costs and the equity that you've built in the home. And you can see that at about 30 years, a code-built house starts losing you money, and it keeps on losing you money until you're like really throwing money away basically by the 60-year point, while the passive house is still kind of trucking along. And so this is on a modest house that costs a fair bit more. Like there's a big premium, at least in our model, on the passive house as compared to the code house, but it's still favorable to the passive house when you look at the long-term picture. And this is another important slide. It's my last slide. And it's about greenhouse gas emissions. And the numbers in the vertical axis are dollars, and those are the costs associated with the social impacts of carbon. So I have no idea how they arrived at these numbers, but there are a number of assumptions that were made about the social costs, so the cost to you and I and our government associated with the carbon emissions. And so you can see, or I can see from this, I want to live in a passive house and I want all my neighbors to be living in a passive house because there's barely any impact from a passive house in terms of dollars of impact on our society compared with the code-built buildings. Seriously, I should have stronger fingers there. And I'm done. And that graphic on the side is a tree trunk cross-section and a human fingerprint, and it's been floating around in social media lately, and I think it's a good reminder about why we're doing what we're doing. So thank you.